adjacent figure is a diagram of the decay of radium-226 into radon. Given that the daughter nucleus is produced in an excited state, write the decay equation and determine A and Z. Since the daughter nucleus is produced in an excited state, a gamma ray is emitted. In this decay, radium gives rise to a radium daughter nucleus, an alpha particle, and a gamma ray. Applying the law of conservation of mass number, 226 equals A plus 4, where gamma has no charge number and no mass number. So A equals 222. By applying the law of conservation of charge number, 88 equals Z plus 2. So Z equals 86. Then we obtain the final decay equation of radium-226.
Part 2. Calculate the energy liberated due to this radioactive decay in mega electron volts and then in joules. The first step is to calculate the loss of mass by subtracting the mass of the products from the mass of the parent nucleus. This gives 5.229 times 10 to the power minus 3U. The next step is to convert the atomic mass unit to mega electron volt per C squared. We will use this equation. So this gives 4.871 mega electron volts per C squared. Now let's use Einstein's equation to calculate the liberated energy. Now C squared is cancelled. Then we get 4.871 mega electron volts. Finally, let's convert this unit to joules. We're going to use this equation. So the answer is 7.803 times 10 to the power minus 13 joules.
Neglect the kinetic energy of the parent and daughter nuclei. What are the forms of the liberated energy? Since we have alpha and gamma emissions, the forms of the liberated energy are kinetic energy of the alpha particle and electromagnetic energy of gamma rays. The energy of the emitted gamma ray is 0.186 mega electron volts. Calculate the kinetic energy of the emitted alpha particle. Using this relation and by replacing each term with its value, we obtain the kinetic energy of the alpha particle.
Let's determine the energy E prime liberated by the decay of 15 grams of radium-226. Remember, the energy liberated due to the decay of one nucleus of radium-226 is 7.803 times 10 to the power minus 13 joules. But what if we have 15 grams? Let's start by calculating the mass of radium-226 in kilograms. This is done by multiplying the mass in U by 1.6605 times 10 to the power minus 27. Now we have the mass of one radium nucleus in kilograms. Now, if one nucleus of radium gives 7.803 times 10 to the power minus 13 joules when it decays. Now, what is the energy produced due to the decay of 15 grams or 0.015 kilograms of radium-226? The answer is 3.119 times 10 to the power 10 joules.
Given that the total mass of a sample of radium-226 is M0 equals 15 grams at time 0, and the mass of each atom equals 226.025410 atomic mass unit. Calculate the number of radium nuclei at time 0. This number is given by the mass of the sample over the mass of each atom. The mass of the sample in kilogram is equivalent into 15 times 10 to the power minus 3 kilograms, and the mass of each atom in kilogram is equivalent to this number. Then we obtained the number of radium nuclei at time 0.
Now we are going to determine the number of the decayed nuclei at time 2400 years. Now we have two steps. In the first step, we need to calculate the number of the remaining nuclei at this time, and then we will calculate the number of the decayed nuclei. So let's start by calculating the number of the remaining nuclei. So we need to calculate small n. We should divide the time by the half-life. This gives 1.5. So replace small n by 1.5 and n0 by this value. So we will get 1.413 times 10 to the power 22 nuclei, but this is not the number of the decayed nuclei. This is the number of the remaining nuclei at time 2400 years. So the number of the decayed nuclei is calculated by subtracting the number of the remaining nuclei from the initial number of nuclei. So the answer is 2.584 times 10 to the power 22 nuclei.
Determine the initial activity expressed in becquerel of this sample of radium-226 at time 0. The half-life is given by ln2 over lambda, where lambda is the decay constant of radium-226. Then lambda equals ln2 over t. To obtain the value of lambda in per second, we have to convert the half-life into seconds. Then 1600 is multiplied by 365 to convert into days, by 24 to convert into hours, and by 3600 to convert into seconds. Then we obtain the value of lambda in per second. Using another relation, the initial activity is given by lambda and 0. By replacing lambda and n0 by their values, we obtain the value of the initial activity in becquerel.
Now we are going to calculate the activity of the sample at time 2400 years by two different methods. In the first method, we are going to multiply the decay constant by the number of the remaining nuclei. The number of the remaining nuclei is unitless. The unit of lambda is second to the power minus 1. Then the unit of the activity should be becquerels. In the second method, we're going to use the law of radioactive decay. Replace each physical quantity by its value. Again, pay attention to the units. The unit of lambda is second to the power minus 1. Then the unit of time should be second. For example, if the unit of lambda is day to the power minus 1, then the unit of time should be days. If the unit of lambda is year to the power minus 1, the unit of time should be years. Okay, so every time you use the law of radioactive decay, pay attention to the units. The units should match. Now the answer is 1.941 times 10 to the power 11 becquerels.
Calculate the average activity of the sample between T0 equals 0 and T equals 2400 years. The average activity is given by minus delta n over delta t. Delta n represents the number of the undecayed nuclei minus the initial number of the nuclei, and minus delta n represents the number of the decayed nuclei, which is equal to 2.584 times 10 to the power 22 between t equals 0 and t equals 2400 years. To obtain the average activity in BQ, we need to convert the time into seconds. By replacing decayed and delta t by their values, we obtain the average activity in BQ.